Let us consider an example problem that can be solved using the economic order quantity model. Suppose we are managing inventory of a product that we consume at the rate of 700 units per week. Suppose also that the order cost is $300 per order, and the purchasing cost, we buy the product for just 85 cents per unit, we buy a lot of the product. Also assume that the holding cost rate is given as percentage as 40% of the purchasing cost per unit of the product per year. So if you hold 1 unit over a year, or whatever number of units, the holding cost will be 40% of those units' value. Now we're also going to assume there are 52 weeks per year in order to be able to convert between years and weeks. So immediately I want you to see that the flow rate is given per week, but the holding cost already is given per year, and this is where we have to be very careful. Right? So if I want to do the calculation of actually dollar value of the holding cost, I need to take 40% of 85 cents, which is the purchasing cost here, right? But if I do this calculation, this would be dollars, right? Dollars per unit per year, because H, 40% was per year, right? So if I want this to be in dollars per unit per week, I still need to convert it, right? I need to divide it by 52, right? So if you divide it, you're going to convert from years to weeks. So if I do the calculation, this is going to be 0.006538, right? Dollars per unit per week now, right? So, right, again, remember R and H must use the same time unit. In this case, I used the week. So how can I calculate optimal order quantity? Well, optimal order quantity is given by the formula Q star, right, equals 2KR over H and then square root. So I'm going to continue calculating it by just plugging in a value for K, right, which will be 300, value for R is 700, and then H is 0.006538. Notice that I'm using a pretty accurate value. Don't be tempted to round this to, let's say, just one digit, 0.007, even though it's a correct rounding in general, right? We round up because it's 5 after 6. So we round it up, but this kind of rounding, actually, relatively speaking, is introducing a large error because, right, it is changing the value 65 to 70, and relatively speaking, this is a big change. In general, when you do calculations, do keep at least 3 significant digits after the first non-zero digit, or including the first non-zero digit, right? So don't round too early. You can round the final result if you like. So if you do the calculation here, it is going to be 8,014.98, and I'm going to just round it to 8,015. It is actually, doesn't matter which way you round it up or down, it's going to be small error and it's not going to affect the cost very significantly. So let us evaluate also some parameters, including the total cost. Let's see, what is the total cost at this quantity? So if you recall, the total cost that depends on quantity is R over Q times K, and that's ordering cost, and Q over 2 times H, that's holding cost. I'm going to plug in the Q star here to calculate the cost at the optimal quantity. And so this is going to be, let me repeat this. I'd copy this and then plug in for R. R is 700, Q star is 8,015. I'm going to put the rounded variant because I want to evaluate the actual quantity that I determined, multiplied by 300, and then again 8,015 multiplied by H. H is 0.006538. So if you do the calculation all the way, first of all, if you do the first part, you will discover that it is equal to 26.2. And then if you do the calculation of 20, the second part, you'll also see 26.20. And this is expected. There could be a tiny difference between those two because we slightly rounded the quantity. But if you plug in the exact optimal quantity, you should get this part equal to this part. The ordering cost should be equal to the holding cost. Because if you recall, we said that at the optimal quantity, the holding cost and the ordering cost should be equal. So this is what we see here. And of course, if you add those two, you're going to get a total of $52.40, and that's per week, right? So, and this is the cost per week, right? The reason this is per week is, of course, because we assumed the holding cost is per week and the flow rate is also per week. Now, another interesting measure could be what is the cycle time, right? We could calculate cycle time, which is Q over R, and that's going to be 8,015 divided by 700, which will be 11.45 weeks, right? It's the length of the cycle. We can also calculate average inventory. I equals Q over 2, right? It will be 4,007.5 on average. Because it's average, we can keep it fractional, and we can also calculate flow time. Flow time, T, will be I over R, which will be equal to 5.725, right? Actually, let's just clarify. I over R, I is Q over 2, and then divided this by R. That's like saying Q over R over 2, right? And Q over R, we already calculated here as 11.45 weeks. So this is going to be half of that, which is 5.725 weeks, right? So these are all the calculations that are interesting for this model. Suppose for the same example, we now have an additional requirement that the order quantity is a multiple or must be a multiple of 5,000. Let's say this is due to packaging. Maybe a pallet or a large box contains 5,000 units, and we have to order 5,000 or 10,000 or 15,000. Any multiple of 5,000 is feasible, but not any other number. Now, our optimal order quantity was 8,015, which is not a multiple of 5,000. So what should we do? So recall that this minimum value occurred at 8,015. And so if we want to now choose a different value, we first have to recognize that it makes sense to try and stay as close as possible to this minimum value. What that means is if I can go to a lower than optimal value, so less than 8,015 will be, the closest will be somewhere 5,000, or I can increase this value all the way to 10,000. Now, I don't know which one will give me a lower cost, but I'm pretty sure I shouldn't go to any other values because, I mean, there's no smaller value, but I could go to 15,000, but 15,000 will give me even higher value, the cost than the 10,000. So it doesn't make sense to choose any other values except the two closest to the optimal quantity. Right? So if the optimal quantity was 8,015, I should try rounding this down to a multiple of 5,000, which will be 5,000, or rounding it up to a multiple of 5,000, which will be 10,000. So I can say optimal quantity will be 5,000 or 10,000, right? But which one actually it will be, I have to first see the cost. So I have to evaluate the total cost, which is given by this formula at quantity Q, 5,000. And also, right, so this is something I need to evaluate. And the other, I need to evaluate the same formula at 10,000, see which one will give me a lower cost, and then choose the quantity that corresponds to the lower cost. So if you do the evaluation, we'll find out that the cost for 5,000 is $58.35, and the cost for 10,000 is $53.69. So first of all, I want you to see both of them are higher than 52.40, right? One is a little bit more than the other. And the reason is, of course, that this one was the optimal quantity, right? A quantity that minimizes the cost. Choosing any other quantity should therefore give us the same or higher value of cost. And second, what I want you to see is that these two components, the cost of ordering, I still did the calculation by splitting, first calculating the cost of ordering and then calculating the cost of holding. So here you see, if we ordered less, we order more frequently, the cost of ordering increased, the cost of holding decreased. It was 26.20 before, right? 26.20 plus 26.20. This one went up, this one went down. Overall, in balance, the total also went up. Here, the ordering cost decreased because we order larger quantity, therefore the ordering cost is smaller. We order less frequently. The ordering cost per week is dropping. And the holding cost, however, is increasing because now we will be holding larger quantities when we, on average, hold 5,000, right? 10,000 over 2 will be average units held in inventory, right? But final conclusion, of course, is important that when we compare those two values, we see that, right, we see that the cost at 10,000 is smaller than the cost at 5,000. So optimal quantity under the new restriction that it has to be a multiple of 5,000, Q is 10,000, right? It's better to order 10,000 because it brings us $53.69 of ordering and holding cost, total cost of inventory.